Now, when it comes to a voltaic or a galvanic cell, remember that this type of cell, this sort of wet cell battery, produces electricity. And so the cathode is the site where reduction occurs, and it's also where the cations of the redox reaction accumulate. Hence, we call it the cathode, right? Where cat is short form for the cations that accumulate. And then the anode is where the anions, and I know it doesn't say that here, but we'll quickly jot that down at the top, where the anions accumulate. And it's where your oxidation occurs as well. So we have sort of a little acronym here, where we know that in the jungle, the Leo says GER. And in terms of what this stands for, well, Leo would be losing electrons, would be oxidation, and then gaining electrons, GER, would be reduction. And then here, when we say Leoa, well, losing electrons is oxidation. That's going to be at the anode. So we say Leoa. And then gaining electrons reduction is at the cathode. Now here's a diagram of a typical wet cell battery. We call it a galvanic cell or a voltaic cell. In one beaker, you have a site where oxidation is happening in the solution. So the solution would be zinc sulfate. And really, because it's ionic, it's really split into zinc 2 plus and SO4 2 minus and then H2O here. And that's all swimming around inside the solution here. And same thing is true for the other site, where you'd have copper 2 plus, sulfate ions, and water all sort of swimming around in here. Now, the electrode in this case, the zinc, which is a solid conductor, this is going to be what actually gets oxidized. And so over time, you would see that this zinc solid electrode, if we leave it in this cell long enough, it would actually get eaten away as your zinc solid turns into zinc 2 plus. So at this part of the cell, you have this half reaction happening. And so we call this a half cell. Now on the other side, the cathode, where reduction is taking place, you have copper 2 plus ions, which this would end up actually being a blue solution. And inside this cell, I would see that this electrode, which is comprised of copper solid, would increase in mass over time. And it would be the mass of copper solid. And it would increase over time if we left it long enough. And that's because the reaction here in this half cell, or the half reaction in this half cell, would be copper 2 plus gaining 2 electrons and becoming copper solid. Now, this salt bridge, remember that your cations are going to accumulate at the cathode, and the anions are going to accumulate at the anode. And the reason, or I should say the mechanism on how that's going to happen largely is going to be through the salt bridge, whereby because there's an electron transfer from your anode, which is losing electrons, to your cathode, which is going to gain the electrons that the anode loses, we have to find a way to balance the charges, because as your anode loses electrons, it becomes more negative as in terms of charge, and as your, I should say less negative rather, because it's losing electrons, and as your cathode gains electrons and then therefore becomes more negative, you're going to have an imbalance on both sides. So to help balance this entire cell, the salt bridge has a solution that has a cation and an anion. In this case, it'd be your K plus and your Cl minus. And so the K plus is going to migrate towards the cathode to balance the charge, sort of as a response to the electrons that it's getting. And then the Cl minus, which would be an anion, is going to migrate towards the anions in response to the electrons that it's losing. And this would be to, again, compensate or balance the charge as a result of the imbalance that occurs when there's an electron transfer from the anode to the cathode. Another point to consider is we got 3 working solutions in this galvanic cell, right? We have zinc sulfate solution, we have the KCl solution, and we have the copper sulfate solution. So how do we know which solution goes where? Well, remember that once you identify which solution has the strongest oxidizing agent, then you know that that's going to go to the cathode. Now, when we have a solution that has the weakest oxidizing and reducing agents, in this case, KCl, so we look at Cl minus and K plus, those are the weakest reducing agents and oxidizing agents. The weakest reducing agents and oxidizing agents are going to be where the salt bridge is. And that's because, remember, its job is just to neutralize the charge or the overall charge of the cell. It is not to be part of the net redox reaction. So if you have agents inside the salt bridge solution that are not the weakest reducing agents or oxidizing agents, then they're going to be part of the net redox reaction. So the weakest oxidizing agents and weakest reducing agents are going to be in the salt bridge here. So if I'm looking at an actual image after this net redox reaction has taken place, this is what I would anticipate to see. The zinc anode, and we knew it was the anode because zinc solid is the strongest reducing agent out of all the substances here. We can expect that to be chipped away and to lose mass, because remember that the reaction is zinc solid to zinc 2 plus, which is an aqueous state, plus 2E. And then we would see that the mass at the cathode would be increased, right? Which is shown over here by the bulge. And while it's showing Cu2 plus here, what it's really actually trying to explain to you is that Cu2 plus has gained 2 electrons and has now become Cu solid, which is a reason why the mass is built up. Lastly, for the signs here, the anode is given a negative sign because of the collection of anions. And so the collection of anions at this spot gives it a polarity that is negative. And for your cathode, it has a net positive polarity because of the collection of cations, which have a positive charge. So let's say we're given a cell like this, and it's a voltaic cell because it's not connected to a battery. This is not a battery, by the way. This is just what we call a voltmeter. So it's just telling you how much volts this electrochemical cell is producing. So, and we're asked to label the cathode, the anode, and the direction of the electrode flow and the reactions at each site. Well, once you know what the cathode and the anode are, then the direction of electron flow and the reactions at each site are simple. So remember that for the cathode, we need the strongest oxidizing agent. And for the anode, it's the strongest reducing agent. So what we're going to do is, given everything here, right, all the solutions and the solids that are given, including that over here, we're going to list all the ions and identify the strongest oxidizing agent and the strongest reducing agent like we would if this was a spontaneity question. And once we've done that, we can identify the strongest reducing agent. And in this case, that would be our Al solid. So we know whichever site has that Al solid is the anode, which would be this site here, right? Because that's the electrode, the aluminum electrode. So this is going to be the anode. And then the strongest oxidizing agent is over here, which is your zinc 2 plus. And the solution that has that is, or the site I should say, would be this site here. Because remember, all these solutions, because they're ionic, they break into their ions, right? So that would really be Zn2 plus and NO3 minus. And so this site here is the cathode. And now the salt bridge, remember, it has the weakest reducing agents and oxidizing agents, I would say. So in this case, your K plus is the weakest oxidizing agent. So the solution that has that, which is over here, would be the salt bridge. And remember, it wants to be the weakest because its job is going to be just to give the cations to the cathode and the anions to the anode. Now that we know what the anode and the cathode is of this voltaic cell, we can determine the electron flow. Because remember that reduction happens at the cathode, so it's going to gain electrons. And at the anode, you're losing electrons. So the electrons that the anode loses are going to be gained by the cathode. So what we do is through the wire, and this is a wire that connects the two electrodes, we're going to draw electrons flowing. So just arrowheads that point to the direction that they're flowing in. From the anode to the cathode, we're symbolizing that the electrons that are lost by the anode are gained by the cathode. And so we show the electron flow like this. And then in terms of the reactions at each site, well, you have an oxidation reaction at the anode, since it's the strongest reducing agent. And then at the cathode, it's going to be zinc 2 plus, gaining 2 electrons to become zinc solid. And what we would anticipate if I were to let this reaction run is that you'd have a mass buildup over here over time, okay, of zinc solid as that's being produced. And then as the aluminum solid deteriorates into, aluminum 3 plus and into the solution, you would assume that this electrode would be chipped away, right, or a bit thinner. And then finally, for the salt bridge, you have K plus and you have NO3 minus. Well, your cations are going to migrate to the cathode to balance the charge in response to the electrons that they're gaining. And then your NO3 minus, which is the anion, is going to navigate to the anode, and it's going to do that via this tube. So what I really should be writing is your K plus through this tube enters the solution here, and your NO3 minus enters the solution here.